about acoustics in ventilation and specifically taming the low frequency roar. But before that, I would like to introduce you to SwegonAirAcademy, who is our objective knowledge sharing platform, and would like you also to pop into our website and look at all the knowledge that we are sharing there about IAQ in specific, and also about HVAC knowledge in general. We publish case studies, webinars, articles and insights, and also have books there. But back to today's topic, acoustics in ventilation and taming the low frequency roar. It's almost a little bit Halloween feeling here the week before. So my name is Norén-Lundh, and I have the honor to moderate this session. And together with me today, I have two of our experts, Tony Olsson, who is the acoustic product manager in Room Unit.
Yes, hello.
And you have been working with this area for around 6 years now?
Yes.
Yeah. And besides him, I have the pleasure to introduce also Martin Ottersten, who is our sound engineer in Kvänum for the air handling units.
Yeah.
But also a visiting researcher at Chalmers Technology University in Gothenburg.
Yeah, thank you.
And we will learn a lot about low frequency and also how we can find sustainable solution to that problem as well, and the challenges. In SwegonAirAcademy, our effort is to raise the tension about the IAQ questions and the different parts of IAQ that we in the ventilation business can affect. And one of the challenges that is maybe of more and more importance as we build better and better buildings is when we install mechanical installations and the acoustics around that. So I'm glad to hand over to you, Tony, to introduce us a little bit in this topic.
All right, thank you, Åsa. I will do my best here. We will start, as Åsa said, with the indoor environmental quality. Most of you, if you listened in before, know that we start with this, and you know what it is. If you're new to us, I'm going to keep it short, but informative. So this is actually a concept where you take a comprehensive view of indoor climate. All these factors that you see here, air quality, humidity, thermal comfort, light, and acoustics, play a big role in the indoor quality or environmental quality. Sorry, the English, I need to come into that. So why? Number one, health. This is the first and most important aspect why we do this at all. Nowadays, we tend to speak more about our well-being and comfort. And in the end, either if we're in school or in work, we need to be productive. So we also speak a lot about productivity. Today's focus will be this cornerstone in IEQ. We will focus on acoustics. So acoustics as part of IQ, just a few more seconds about that. What is acoustics, environmental quality? I'm going to do like this. Picture yourself in auditorium, conference room, or a lecture hall. All these different rooms have different needs. What we like to have is a positive sound environment. But it doesn't necessarily mean that the noise levels should be as low as possible. It also happens that we add sound to mask other sound or noises. However, the cornerstones is sound level, frequency distribution, and reverberation time. These are very important to create a positive sound environment. I highlighted here the frequency distribution as we will cover that kind of more or more in detail. We will speak a lot about it. We will try to give you a red line now from frequency distribution out to what we can do actually with the noise sources. So if we start at frequency distribution, I want you all that are listening again to picture yourself, because all of us, I'm sure, have experienced a thunderstorm, right? And what we actually do back home, me and my family, is when you see the lightning, you count the seconds from when you see the light until you hear the rumbling noise. So 1, 2, 3, 4, 5, 6. Let's say 6 seconds. You hear a low rumbling roar. But occasionally, the thunder or the lightning can strike very, very close to us, and you will experience a different sound. You will probably experience a high, crisp sound, a kind of scary. It's like ripping a paper. So what you hear is different frequency components of the thunder. And why is this happening, and why do we hear a low rumbling noise if it's far away? Well, it tends to be like this. The low frequency sound with very long wavelength travel far, whilst mid and high pitch frequency tend to get attenuated, reflected back on material, so it gets lost on the way, you could say, oversimplified. And talking about thunder, either it makes you scared, maybe a few things, you get a happy feeling to listening to the thunderstorm, I don't know. But the thing is that if we take sounds like waves that we see in the image, which I consider to be a positive sound, it could be inspiring, calming, happy, or at least with music, I can feel very happy. My point is that sound will create feelings, and we will speak and dig down to some case studies just shortly. On the other hand, we have the man-made kind of noise sources. So illustrated here, just some example of sound sources with more or less low frequency components. And already now we speak about not only frequency distributions, we are digging down to the low frequency part of the noise, which we will cover mostly today. It could be all kind of transportation. Speaking of heavy transportation, engines, wind turbines, mill, compressor, and such, pumps, all the way to the fans and ventilations, like an air handling unit. And just the air handling unit, we will see some studies and research around today and potentially what we can do. But before we dig down there, let's just cover some keywords within the area. I will open up each of these. Start from vibration. If we start from vibration, we have a sound signal going in a medium like air or water, which creates pressure waves, right? Yeah. It enters our eardrums and gets the input to our brains. So we hear the sound and we can picture the sound, you can say. Now, shortly, frequency. Frequency is just the number of wave cycles per second. Hertz, it's what you normally write. It could be low or high pitch sound. Low if you have a bass voice or the rumbling thunder, or high pitch. Now, sound or SPL, also something we speak a lot about in correlation with sound, or we need to do, is a sound pressure level. It's a loudness or strength of the acoustic signal or the sound. And decibel in shortly is logarithmic unit. It's a ratio. It's a ratio between, in this case, when we speak about sound, a threshold, which is 20 micropascals. So why am I telling you this? Well, actually, there's a strong correlation. We always speak about, we always need to know the level of the decibels when we speak about frequency, or the other way around. If we speak about the frequency, we need to know the amplitude of the sound. For example, if we have a sound that is 80 decibels at 20 hertz, we can barely not hear it. Then it starts to get hearable. But if we have a sound that is 80 decibels at 4 kilohertz, it will be loud to us. So the frequency component is always important. Now I spoke about the wavelength, which also is an important part, and we're going to speak a lot about wavelengths actually. It's actually compressed and thinner air over a period of time, which creates a length of the signal, you can say. The amplitude might be the same as a shorter one. Like, for example, in this case, when we speak about low frequency sound, we speak about a range from 20 hertz to 200 hertz. Or I will do it. Martin will switch that a little bit when we speak about the air handling unit. That corresponds to 70-meter wavelength up to or down to 1.7 meters. Now, I give that information because these will make some challenges for us. Before we speak about challenges, just a few words also about noise criteria. Because somewhere in the end, we need a criteria to understand the level of the sound and how it affects us, or need to have a criteria to be verifying something to measure against, like a European standard, ISO, ASHRAE, or a national standard. Depending on where in the world you are, you might encounter NC, NR, dBA, or dBc. By a short example, if we look here in 8 octave bands, ranging from 63 hertz up to 8 kilohertz, which is standard in the HVAC industry. We will figure out how much that sound will be in a single value using these 4. So this is just the air handling unit for residential use, a smaller one. We can see that we have a lot of the energy in the low frequency area. And down to 63, we see 66 decibels. But okay, how does that translate into, for example, dBA? Well, we do a filtering to reflect our ear and the way we listen to sound or hear the sound. We are not that sensitive in the low frequency area as we are in the high frequency area. So we filter out a part. If we take the dBc, we do not filter much at all, and you will just get a higher value, still the same sound, but a higher value. If you take NC or NR, in this case, is more of a holistic view, which means that it considers each and every octave band here and have that as a limit that you will have to be under, which means, for example, NC gives just a value of 50, which is kind of a noise rating value. It tells you how much noise you have in each octave band, whereas the NR, quite similar, 51. But if you experience this, or if you see a few of them, you should know that they exist, several of them, and they will differ, as you see. All of these values, 56, 68, 50, 51, point at the same sound. But it tells us also information what kind of frequency distribution there is into the signal. Okay. I'm jumping further now. What about outside the hearable spectrum? I said that the hearable spectrum is approx between 20 and 20,000 hertz. Well, outside those limits, we have something we call infrasound. So below, even though down in the very, very low hertz range, we have the infrasound. Whereas most of you have heard ultrasound, I guess. It's the very, very high pitch sound, and we human beings cannot hear it anymore. Few animals can, but we cannot. I will just mention it here because we will come back to infrasound as well in an interesting part. Now, just some few challenges as well about the low frequency sound, starting with a building. Okay, what would be the challenges within a building with low frequency sound? And now I mean again 200 hertz and below. Probably 63 hertz and below will be the real challenge for us. Well, low frequency sound tend to propagate more easily into a building due to the wavelength. It's a very long wavelength, which means it penetrates walls, floors, and ceilings more easily than high-pitched sound. and also can create structural vibrations, which means that a room inside a building could be like a transmitter. Okay, so somewhere else in the building. So, and the challenge here with the low frequency noise is that it travels in the structure in the building. So if it gets introduced into building and it's too high, it can create problems for us or a challenge. Now, if that happens, we get complaints and someone calls in and would like to have a measurement. This is also very difficult if you look into a building. To verify the sound levels, if there is a lot of portion in the low frequency, is demanding. Because, again, long wavelengths can create something called standing waves within a room. That means that in one point, you can measure 20 decibels higher than another point. So you really need to know what you're doing when you do these measurements, to understand that you measure correctly. And also one challenge is if you go in there and measure with a dBA, you filter out a lot of the low frequency. So even though someone experiences a problem or complain, the one that do the verification might be within the limits anyway. So this could be a challenge. Just shortly, also for us to create product data is challenging with the low frequency signals or sounds. Because designing, simulating, and testing all sounds is a challenge that not everyone is able to take up, especially when we are at, 63 hertz and below. I said we are having product data from 63 up to 8 kilohertz. Yes, we do. And we spend tremendous lot of time testing our products. Now, the real challenge is if you would like to go further down and measure and verify also 32 hertz or even below, because you need to be large or very, very large laboratories. You need to shield you from background noise. You need to have ductings that are big, huge system. And not sure if all the test standards support all the way down to very low hertz. So it could be a challenge for us. And if introduced, I do like this. If we have a sound source where we need to attenuate, and now again focusing on the low frequency, it's tricky for us. Because normally we need to have very thick attenuation material. We need narrow air gaps. And we need a huge attenuator to get at least a good number of attenuation in the low frequency. What does this mean? Well, we need to actually, if we need high attenuation and compact measures, we can stuff the channels, we can close it, but you have maximum pressure drop. So we could stop the signal, but the air needs to pass through, not the sound. So it's always this game when we are developing the next generation attenuator.
And low pressure drop is important. So
low pressure drop is important because else the silencer in itself could be the noise generator in the end. So yeah, many things there to get into the mechanical room if it should be a very effective one, and not if we look in sustainability either. So,
but what if we what do we need to take care of then with these challenges with the attenuation? Because we need to have the air pass through the ductwork, don't we?
Yeah, the air, of course, need to pass through. And today there is different solutions. The most common is to have baffles in the duct, right? Yep. With as thick material as possible. In the end, this will create pressure drop for us. And pressure drop is not good because it costs us energy pushing the air through. So that's one part of the story. And the other is to design the system so we don't need the large attenuator directly after, for example, air handling unit in this case. So the design that directly after you have a certain sound level that should be acceptable. So that this is something acoustic people always calculate.
Great. And then we have looked into the background here, Tony, with the standards and sound criteria, the nomenclature for frequencies and sound pressure level, etc., and the IEQ. But what happens to our health and how does it affect us? Martin, you will dive into that and talk a little bit about the sick building syndrome.
Yeah, exactly. Oh, now you said the word, so now I don't need to say it.
Sorry.
You said that low frequency is a challenge. For me, it's an opportunity to have something removed. So I see it as an opportunity.
Great. Yeah. Me as well sometimes.
Yeah. Can a building be harmful? Picture yourself walking into a building and suddenly you feel an unexplained sense of discomfort. But when you leave the building, the previously felt discomfort will disappear. And this is what's called sick building syndrome, SBS. SBS was coined by the World Health Organization in the 1970s. It's a range of symptoms that can occur after spending time in a particular building. And the symptoms are headache, nausea, fatigue, shortness of breath, eye irritation, and skin irritation. And for these symptoms, they usually disappear or reduces when you leave the building, and they go away. There are a lot of studies on SBS, and the early studies said that it was due to poor air quality. But other studies say that it's the same factors that Tony talked about when he talked about the IEQ, which is the air quality, humidity, temperature, light, and acoustics. So they are connected. But new studies have shown that it's also noise is a significant factor.
Okay.
And especially low frequency noise. And that's why we have talked about low frequency noise.
But how common is this sick building syndrome? How many buildings have
according to World Health Organization, it's like 10 to 30% of the new and renovated buildings.
So of the total building stock? Yeah, that's quite a lot.
It's a lot.
Yeah.
It's according to World Health Organization.
Yeah. But on the other hand, I guess the part we can't decide what is then the acoustic part of that.
No, because it depends on which studies you read and what the study had for direction when it started the study. So it's hard to tell.
And do we have you looked into the different research about this problem in your fields?
Yeah. I've read many different research reports and studies about. I've tried to read as much as I can about the low frequency areas. And I do the same findings as you do here. So you see these in most of the records regarding low frequency sound or noise.
So we go on. Should we?
I can take that one just shortly. I'm going to skip out like this because, like I said, I've done we have, you as well. Yeah. We're reading plenty of studies. We would just like to sum them shortly. Noise does affect us. Yes, we spoke about that. But the annoyance is highly individual. So some people are not annoyed at all.
Okay.
And this is difficult when you read the report that someone is not annoyed and then we have a 20% that is annoyed. So it starts to get into the 20% kind of annoyance rule here. But it's highly individual. We are different sensitive to sound. Yeah. These researchers are done in different ways and the exposure of the sound is coming in different ways. So it's not easy to read one report to another and compare them to each other. There is fewer studies on low frequency part of the sound.
And maybe that's natural because it's hard to measure as well.
It's hard to measure and actually we do not sense it as easy with our ears. So the amplitude needs to be quite high for the SPL that we spoke about. Even though it spreads, so we could have annoyance in another part of the building caused by a mechanical room here.
But I guess buildings have installed mechanical installations, HVAC industry, amongst others, installations, electricity, and so on. And we are developing our building, we are insulating, and we are developing our technology to be as quiet as possible. I know, Tony, you have been talking about electrical cars and how they have been working with the fans and development of that.
Mm-hmm.
But what about the fans in the HU, and how can we solve the problem in a more sustainable way, Martin?
Yeah, so then we talk about the sources, the possibilities, as we said. So we have done some studies on low frequencies generated by air handling units. I have done them at Chalmers, where I'm visiting researcher, as we said. And we do this by simulating the air handling unit or the fans in the air handling unit. And this, for example, one of these studies, it took 3 months for 300 computers. So it's a quite time expensive and computer expensive simulations.
But that is quite impressive. 300 computers simulating this.
24/7.
Yeah.
So it takes a long time. An air handling unit is a typical sound source, as we know, both broadband and tonal. And it's the fan that produces the most part of the tonal noise in a ventilation system. And it's also the tonal noise that affects the IEQ and the SBS most.
Mm.
So it's important that we can take away these tones. If we take a look at the spectrum of one of these commonly used centrifugal fans, it looks something like this, where we have 2 tones here in green. And what are these tones? They are the so-called blade pass frequency and its first harmonics. And the blade pass frequency was coined before, when we have a casing or a volute around the fan.
Yeah.
The blade interaction between the guide vanes and the volute cutoff, they generated this blade pass frequency tone. But we removed this casing or the volute a long time ago in the industry, but we still have this tone.
Mm.
And until my study, we had there were no real source developed, or they haven't found the real sources. So that's why I started my study on this.
Huh.
And it's connected to rotation speed. It's the rotation speed times n, which is the number of blades, divided by 60. And then you get the frequency of this blade pass frequency. And in a modern ventilation system, it's commonly in low frequency range. And low frequency, I talk below 500 hertz.
So now we're a little bit higher.
Yeah. To give you my studies, we need to start to understand the fan. Otherwise, you wouldn't understand the study. So we start by understanding the fan.
That's a good start.
Yeah, I think so. So take a look at the fan. It looks like this, the fan in gray and the inlet duct in green. And it's a centrifugal fan, meaning that the flow is going in an axial direction and then it changes direction to a radial. And that's why it's called a centrifugal or radial fan. It looks like this. And if we zoom into the region between the rotating fan and the stationary inlet duct, we have a gap marked here in blue. The pressure, it's also here. And the pressure outside the fan is higher than the pressure inside the fan. And due to this pressure difference, we will have a flow entering the fan like this. So we have gap flow, we call it, here marked in green. If we take a look at the left picture, we see that it goes into the fan through this gap and it moves out with the main flow. So now we can go back to the study. So we start with the first study here on the blade pass frequency, which was my PhD thesis, which I defended 1 year ago.
Yeah.
And now I will sum up it in 4 pictures. So 5 years of work in 4 pictures.
Yeah. That's very smart of you.
Yeah. Or a bad study. When the fan starts to rotate, it generates a tone, as we said. And this tone can actually have the effect on humans. You can actually have cardiac arrest. And if we take a look at one blade, and here we see the leading edge of one blade, and we also see the gap. And it's the gap we talked about, and we have the flow into the fan through the gap. And when we have this flow, it generates turbulence, marked here in orange, black, red. And if we zoom into this turbulence, and now we color it in blue, and I like to call them worms, because I think they are like small worms or snakes.
Very cute ones.
Yeah. And we see here that we have an interaction between the blade leading edge and one of these turbulence worms. And we found that this interaction generated pressure fluctuations. And we know that pressure fluctuations are noise. So in my program, I can set, I want to see at which specific frequency where I have the largest pressure fluctuations. And that's what we see in the fourth picture here. So we concluded that the sources for the blade pass frequency is this interaction between the turbulence and the blade.
So in this part of the study, you really identified where the problem is.
Yeah. So this was the first of my study, and the second part was to remove this. Let's talk later about that.
Yeah.
We know that the fan also generates other frequencies. But as we said before, Tony, we need the fan because we need the fan to move the air.
Absolutely.
So we cannot get rid of the fan. We need a fan.
Yeah.
We will go now even lower in frequencies. We will go to what Tony talked about, the infrasound.
The infrasound.
And there are studies where I have read where they saw that infrasound and its connection to the SBS. It was actually 7 hertz, and it affected the SBS. So again, picture yourself walking into a building, and suddenly you feel this discomfort. But this time you hear no noise. And the air quality seems to be good. And when you move out of the building, the discomfort will disappear. And that's the problem with the infrasound, as Tony talked about. We cannot hear it. We can just feel it, and it affects.
So it's a bit spooky in one way.
Yeah, it's a bit spooky. Yeah. And we wanted to know more about this and knowledge and understanding about this. So we did another study on this, the study of the infrasound. And again, we need to take a look at the fan.
Yeah.
And we see the main flow here in black. We have the gap, as we talked about, and we have the gap flow here in green. And if we take a look at the gap flow in my simulations, it looks like this. So here we have simulated a fan. We stop and we take at the exact same time, we take 2 different blades, and they will look like this. So if you take a look at the left blade, we see that there is an orange region where it's a separation. So the flow is going in from the gap and until it comes to this position where we have the orange region where we have flow separation. So the flow leaves the blade here, and it also divides the flow. But if we take a look at the right-hand side, the blade, we see that the flow is going smooth around the blade. And this separation generates pressure fluctuations, and pressure fluctuations are
sound or noise.
Yeah, perfect. You can take over.
Yeah.
So we wanted to see how these pressure fluctuations affected and what happens. So we take a look at the fan. Now you know this fan. We add a plane here in orange. And on this plane, we plot the pressure. And then it looks like this. It's a lot of colors. You all need to focus on the red color. So here are the red color. It's a high pressure. Then we start to rotate this. So here we have 0 revolutions, and then we rotate it 5 revolutions. And we come to this, and we see that the high pressure region has moved a little bit. And after 10 revolutions, it has actually the high pressure region has rotated a half revolution.
Yeah.
And 15, and then we go to 20 revolutions. And here the high region, pressure region are back to the same position as 0 revolutions. So the high pressure region has rotated 1 revolution for 20 fan revolutions. To sum up these studies, the blade passing frequency is connected to the rotation speed, as we said, but also this new infrasound frequency tone is also connected to the rotation frequency. And here we have the equations for them. And in my study, I used 2,800 RPMs. And if we calculate the frequency, they will be like this. The blade pass frequency is at 327 hertz, and the infrasound is at 2.4 hertz. And this is extremely low.
Yeah.
We couldn't measure it with microphone. We had to measure it with vibration meters. And if we calculate the wavelength, it will be 1.5 for the blade pass and 133 meters.
Yeah.
And I mean, building a attenuator for 133 meter, it would be impossible.
Yeah.
Yeah.
Great. But what does this mean then, Martin, for your development of products and future HVAC systems?
Yeah, this will mean I was just start with the title of this webinar was Taming the Low Frequency Roar. And now we have the knowledge, we have the understanding of the fan. And with this knowledge, we can now, or we have designed a new fan where we have removed both of these 2 low frequencies.
That's really exciting.
Yeah, I think so. You see, I'm shaking.
Yeah.
And with this, I just want to say that we haven't tamed all low frequencies, but I think we have made the lion kinder.
Yeah, and it means that you can do this in a more sustainable way than trying to build in a large amount of equipment to solve maybe a problem in a building in that way. And we get smarter, greener building and healthier building.
Yeah, absolutely. I mean, we need less attenuators, which will cost less pressure drop and less energy. So I think it's a win-win to get to the source and remove the source instead of just adding.
Absolutely.
But so that's a positive future for the future development in HVAC business and for installations in buildings. But why are we talking about this, Tony? To come back a little bit to the question I put to you earlier. Are we getting questions about these low frequencies and how does it look in the future? We got a question in the chat actually about that. Will this be something that will increase or decrease in the future? Hopefully decrease then with new installations, but what do you say?
We, as well as other industries working with fans, and then I mean industries like electrical cars or maybe computers, you have fans everywhere. And everywhere we work with the fans to get them to be quieter. My point of view, looking a little bit into the future, is that we need to care even more shortly about this due to some factors. If I may jump a few slides, I actually prepared some points here. So thank you for the question in the chat. I see we are running out of time. I'm going to do like this. I did prepare a slide, so thanks for the question. 2 points that I see. One is that the building envelope is getting very good at blocking outside sound away, which means we get sensitive with the sounds within the building. Low frequency noise, one, high pitch, another. It could be any sound really, but the low frequency sound tend to spread really easy, as we spoke about in the building. So this one is more important. So I'm happy to see your research and hope we can. I actually hope that I'm unemployed one day.
No.
If the fan's getting so quiet, because it's not really necessary. It shouldn't be necessary.
But we have other sources.
We have other sources to have a fine air handling unit and then immediately start to blocking the air passing into the building.
And then we have sound issues locally.
Then we get local sound.
And so on.
Yeah. So it's not an easy task. The other one about your question is the uprising of wooden construction. No, because we have done this for many years. All the buildings in the world today, we hear some part of them have problems with the SBS. Most buildings have no problem at all. Very perfectly fine buildings built in heavy concrete.
Yeah.
Heavy concrete is a good material to actually block away also the low frequency in some sense. Yeah. Moving towards wooden construction or lightweight building, you take away mass in the structure. We will have a challenge. Definitely, we will have an acoustic challenge, or we will have to agree upon maybe a higher level of sound within a building. It is my belief.
Or be very careful in the design on the installation part, how you...
Exactly, on that part as well. So there I think as within the car industry, because within an electrical car today, it's kind of quiet within the car. I know they work extensively with their HVAC system in the car to keep it quiet, right? Yeah. But with that said, and the time is running, we got a little delayed, or we did a recap from the start.
Yes.
That was planned.
That was planned. I would like to take the opportunity to just make some conclusions. We have read a lot of studies and research that they point in different directions, but for sure, and we know that sound affects us. We know that because I guess everyone knows that because we hear and sense it all day long, all the time. Today. With today's future trends that we see, and especially those I just spoke about, we need to address and beware of the sound. So this area will be very important. It's ongoing right now, and each week we have phone calls and discuss this with each other and help customers that will potentially have this problem, how to solve the issue. So to finalize, I think with continuous development of noise sources, like you presented, but also noise control in the other end, we will be fine. Yeah. We will be fine.
Great. I wanted just to take the opportunity to ask you 2 questions that have popped up in the chat before we wrap it up. What are the other sounds and noises and vibration that can potentially harm us, and what are they being created by the mechanical systems in the building? Can you give some examples?
I would like good question. I would like to remove the word harm us and affect us, annoy us maybe, because there's a lot of the sound in the building. One very common that you will notice is the water side. If you have radiators or ceilings with water pipes, so valves tend to create the irritating kind of high pitch sound, which I see a lot.
Yeah, and that could be like a webinar on its own, I guess, the hydraulic system and the noise from that. So I might invite you back then, Tony, to talk about that.
I was about to say I would like to listen into that one, but maybe if I present it, I will learn even more.
Yeah. And then for Martin, we have a detailed question. Why aren't the red noisy regions created by the fan created symmetrical around the fan? Why don't they spread out symmetrically around the fan?
Why it's not? Yeah, and that's the problem. I don't know if I can go in too much detail, unfortunately, on why, but
because you have a patent pending for this one, so
the solution for it will, if I tell you, then you have the solution for it.
Yeah, so then maybe we should really come back to that after a while, maybe in a year or something, and we can talk more openly about that, the interesting part. So good question from Frederick. So I see that our time is running up, so I would like to take the opportunity to thank you for doing this presentation. Sorry about the technical problems, but you did a great recap.
Thank
And
you.
if there are any questions after this webinar, you might send them to SwegonAirAcademy. You see the address and contact on our webpage. And we will also publish the video of this webinar on the website later on, so you can go back and listen in. So thank you very much for doing this together with SwegonAirAcademy today.
Thank you very
Thank
much.
you.
Thank you very much for listening.
Yeah, thank you.